So, complementing what was been said by Angel and Richard, I will dwell a bit more on the tritium breathing blanket. And okay, to start with the major functions, of course, and we have all heard that already today several times, but to be complete, as the name says, first function is to generate the tritium that is not available in nature. So very important part of the fusion fuel. There's the interesting question of and then how to start the reactor. If it's not available, I'll come back to that question tomorrow in the supply chain talk. Then, equally important is that the breathing blanket has to harvest the energy that is produced by the fusion reaction. I think Angel already mentioned this. I'll come back to that. And finally, specifically in magnet fusion. Inertial fusion, it's a different situation, but in magnet fusion, the breathing blanket has also the additional function of shielding the magnets that are surrounding the reactor. These are the three elements. Now, I'll go a bit more in detail, starting with the tritium production. So we already have seen that tritium can be generated from lithium. This is in a nuclear reaction using the neutrons produced in the fusion reaction. So actually one fusion reaction on the nuclear level consumes one tritium atom and produces one neutron, and theoretically this neutron then produces a new tritium atom. Theoretically. In reality, of course, we lose quite some neutrons through wall openings, through unwanted reactions with structural materials, with the coolant, and so on. Therefore, we need, of course, neutron multipliers to compensate for the losses. This can be, for example, beryllium in the one or the other form, or it can be lead compounds. Speaking of the form, also the lithium has to be provided in the appropriate form. We are talking about lithium-containing ceramics or lithium alloys or lithium salt, the two latter in a molten condition. Anyway, all these forms are less corrosive than the pure lithium at high temperatures. Then, of course, we may need isotope enrichment. And as like for the startup supply, I will come back to this aspect tomorrow in the supply chain talk. Then, of course, and Richard mentioned it already, the generated tritium has to be extracted from the breathing blanket to be useful. And the various techniques there depend, of course, on the overall concept. For all of these things, the breather material, the neutron multiplier, the extraction technologies, so far we have single effect experiments showing that it could work. But we have no combined integrated testing. This is the major deficit at this moment. And that means that the technology readiness level is quite low so far. I could talk about a level of 2 or 3. And here, of course, we have to work on. The second function, harvesting the fusion energy. So 80% of the fusion energy is being taken away by the neutron. This is just following from the law of momentum conservation. And so we have neutrons of 14 MeV energy. And this is almost one order of magnitude more than we see in fission reactors. This is important to note. And so these neutrons, of course, deposit their energy in the breathing blanket via collisions. But this needs a stopping length of 1 to 1.5 meters. So that means we always need this dimension for the breathing blanket, whatever shape it will take. Okay, there are some very sophisticated approaches with neutron reflectors, and the situation could be a bit better, but in general we have this stopping length, and this also has to be taken into account if we try to decrease the size of the reactor, because this will not decrease. So, unfortunately, the neutrons do not just produce tritium and deposit energy. They also initiate various kinds of damages. First of all, I'm talking about the structural materials. There are other aspects. The structure, of course, is filled with then the breeder and the multiplier and the coolant, and all this makes a very complex situation that we have to consider. But coming back to first of all, to the structural materials, the neutrons can knock out atoms from their place in the structure. This is the so-called lattice. This so-called displacement damage accumulates, and of course, more or less, depending on the temperature of the exposure, but you cannot avoid it completely. And this limits the lifetime of this component, and that means we have to exchange it regularly. But it makes a big difference if you have to exchange it every year, or what we are targeting is a period of 5 years. Unfortunately, displacement damage is not all, and neutrons also obviously initiate nuclear reaction, like the generation of tritium from lithium, but it's not the only one. There are also so-called transmutation reactions, which often result in the release of light atoms like helium and hydrogen, which tend to accumulate at the grain boundaries of the structure and also limit the blanket lifetime. There are approaches to overcome this, but with respect to the time, I will not dwell on this. And above all, the transmutation reactions can generate unstable atoms, radioactive atoms. And this has two consequences. First of all, the blanket exchange has to be done by remote maintenance, and we need specialized materials to avoid long-term radioactivation. This is the difference to fission, and it's what we always stress. And such reduced activation steels have been developed around the world. I also come back to this during the supply chain talk. So then the structure is necessary to construct the breeding blanket, but in itself it does not extract the heat. So we need a coolant, Ankel mentioned that, at possibly high temperature to extract the energy. And so we know, for example, water is a coolant from the pressurized water reactor concept, but fusion is not fission. And so, for example, pressurized water reactor means 325 degrees to maintain the distance from the critical point of water, which is around 375. Now, otherwise you get two phases of water and the so-called water hammering. You absolutely do not want to have this. Now we have the problem that the structural materials, the steels at least we know so far, would need an operation temperature of at least 350 degrees to avoid this accumulation of damage. So we have a gap here. The other option is helium, which is, let me say, less developed, would take more time to finally come to something useful, but would avoid all the difficulties with corrosion, activation, temperature. Still, it could be quite expensive and scarce in the end. I know that in China they are now looking at CO2 instead of helium, but this entails new problems. So Now I see time is running out. I just would then speak about the third function, that is the neutron shielding, obviously only necessary in magnet fusion. It is less complex than the other aspects. It just requires to bring in the right materials and the necessary building strength. So from what I told you before, you can imagine that designing a printing plate, taking into account all the requirements and limitations, and also the manufacturing aspects, poses a high-level engineering challenge. And solutions for individual aspects have been developed and verified. What is missing is going to higher integrated systems with more relevant environments and operational conditions. And this, so far, has been limited by the availability of funds. I keep saying, as long as plasma physics is in the center, in the focus of fusion research, so long the power plant will always be 30 years ahead. So we can see that a change has started to give more emphasis to technology, but this has to be increased. And in this sense, the realization of IFMIF donors here in Spain would be really a change in paradigm, but of course it is not sufficient for all the validation and qualification tasks ahead. We are very close to this, starting this, but still it has not yet been fully decided, but I hope that this will happen now soon. Thank you.
Klaus, thank you so much.